Hi, I'm Tom and I talk about code. Today, we are going to be building some tooling for our PlayStation 2 engine. In the previous streams, we've been working on indexed textures, so we can now load textures and draw them with a color palette set in the PlayStation 2 hardware. This means we can load really compressed textures. It's going to be great for our VRAM efficiency, but the problem is we don't actually have a way of generating image files in a format that can be loaded, right? Image files with indexed color. So let's head over to my screen. I've already conveniently drawn some of this stuff. It's almost as if I started talking about this and just didn't have my screen shared and then had to start over. Crazy. So if we have a TGA file, right, you've kind of got some kind of header, you have some like metadata, which I think is optional, you get a color map. I think this is the order these things go in. You have the pixel data, which is the stuff we usually care about. You have a footer, which was causing us a lot of grief in a previous stream. For people who remember that, I was reading this footer and overriding my buffer, and it was like overriding some really important memory. Anyway, pixels are what matters. If we go over to a sprite, here's a fun test sprite I've drawn. I'm still using the Pico 8 palette because that's fun. And let's have a quick tinker with the palette, right? So a color palette, it means we can do something like this, right? We can shift these colors around, we can change what the palette actually means. But when we save this in a sprite, it just saves a true color TGA, right? It doesn't save the palette information as well. Unless there's a way to make this happen in a sprite, but even still, I think it makes more sense for me to work in true color sprites and then export them, and then kind of, pre-process them in my asset pipeline into formats that I want. I think that's going to be more flexible in the long run. Maybe not, but we're going to go with this for now. Or, I mean, maybe even, well, I don't know. We're going to assume everything is a TGA at rest for now. So, kind of at build time for our program, right? So if we look, for example, at the moment, we have an asset folder. We've got these .obj files. And these .obj files get processed into .bin files by a script that I wrote in asset pipeline. I've got a script, it loads an object, it goes through, it just pulls out the raw vertex data and color data, but in this case just zeros, and it dumps it into a really dumb list. So what this means is the PlayStation 2 code doesn't have to worry about what an obj file is, it just reads dumb vertex data, and it's so simple and it's so easy to go. So we kind of do a pre-processing step here. So in this pipeline today, we're going to write another script for loading a true color TGA, pulling out palette information. And I'm thinking about what this means, right? So maybe this means that we have to supply the tool with a palette and an image, and it will give us back an indexed image, or crash if that image can't be applied to that palette. That's where we're going to start. So we have already got a TGA file. So the first thing to do is to parse a TGA file, right? And we've already done this in C, so I'll pull up another terminal, 3D test, TGA.c. We've already written a TGA parser. This isn't going to be quite as simple in Python. In C, all we've done is actually define this header struct in such a way that all the bits are tightly packed together, all the fields are tightly packed together, and then we just read it out. Unfortunately, in Python, I guess we can do this, right? We can use the struct library, right? Python 3 struct. Let's have a look. I think also one of my goals for the pipeline was to not use anything outside of the Python standard library, right? To not have to like pip install anything. So yeah, I think we can do this, right? I think we can. Yeah, cool. HHO, yeah, so we can just have an arbitrary stream of bytes and we can unpack that. So let's try this, right? So let's go TGA.py. Also, just as a quick note, I've made a new branch here called pipeline TGA Index. This comes off of my previous branch for the color lookup table work, but the color lookup table work, we can't really merge that in if we don't have a way of actually loading and handling indexed color textures. I've done tests where I just like generate textures in memory, but I'm not sure they're quite thorough enough. I want to test a pattern like this to make sure that everything is working properly, that the order of pixels in my buffers is actually equivalent to what is going onto the screen, and I can really only test that if I can load some example texture. So we're going to work with this texture, and we're only going to consider the color lookup table work complete when we can actually pre-process and then load index textures like that. Another quick note on TGA files, right? TGA, not the stock, TGA file. There's a great wiki article that goes into That information seems to have come from Wikipedia, but doesn't link. Cool. There are a few good sources for this. Wikipedia does it pretty well. We can create an image, a TGA file, which actually contains its own color map, which is interesting. I don't know if we're gonna actually do that. We may just not include the color map, right? We may just like leave this empty. I don't think we're gonna read it anyway. Anyway. But yeah, the image ID field has some information here. So you have a header, you have some other stuff. Have I assumed that this is all? Okay, well, look, let's get the actual specification up, because that's going to be a little bit better. I think we read the whole header before any of this extra stuff comes into it. And also in this parser, I'm assuming that ID length is 0. I think I explicitly check that, maybe? I don't explicitly check that. So if ID length isn't 0, and if the color map type isn't 0, and the color map length isn't 0, then this parser will actually fail, right? Because there's extra stuff here before the pixel data that we're not factoring into account. Cool. All right. So TGA data formats, right? Or data types. At the moment, we're working with uncompressed RGB images. We're going to swap this over to uncompressed color mapped images. And we're going to have 1 byte per pixel. Even for data where we have less than 1 byte per pixel, we're just going to say it's 1 byte per pixel. Maybe we could simplify this more. But anyway. Actually, we do have 4-bit images as well. Maybe I need to hack this to have other stuff. Maybe I just need my own image format. 32, 33. Well, so the format is specified by a byte. So we could just use values way out of this range, right? Like, there are only a few values here. I'm guessing this is a bit thing. So if bit something is set, maybe not. Anyway, this is all a bit neither here nor there until we actually have a TGA parser. So TGA.py. We're going to pull in the struct header. Pack, unpack, yeah. So let's go. Do we make a class for this? Do we want a class? Do we just want functions? Let's just go with a class for now. We're going to give it an array of bytes. The header is going to be, so what's this? So let me go by the spec rather than my potentially faulty implementation. Okay, so the first 18 bytes are just this stuff, right? So, yeah, and then we have color map specification, image specification. Okay. But the color map specification... Alright, interestingly, yeah, so this actually calls out what this is. That's really good. We should also think about parsing run length encoded taggers at some point. Okay, so let's start pulling this stuff out. Let's go... cool. Something... I have caps lock on. That would explain it. So let's make a variable for what this header is. Let's say header equals. So this is, now we need to just quickly check a struct syntax. Does this actually, yeah. So signed car, unsigned car. We want unsigned car. Color map type is a B. So these are all 1 or 2. So what's a short in this? 1, 2, short, H, or capital, probably capital H, right? B, 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 H, H, B, so B, 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 H, H, B, H, 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 B, B, And then we're into varying data. Cool. Dark reader extension. Is that an extension for Firefox, you mean? Because reader view is something that I use a lot and is actually pretty awesome, and I probably should use more when I'm streaming. But anyway, oh, I need to fix my webcam as well. Hold on. This is important. I've realized that this actually, and sorry if this bugs out a little bit. So this looks worse, right? But then ready? That should fix the flickering for some reason. Dark reader makes every screen have a dark mode. Yeah, that's cool. Does every texture have its own color indices, or is there one index for every texture on the screen? Every texture has its own... every texture can have its own palette. One texture can have multiple palettes. It's very, very flexible. But yeah, no, absolutely not one palette for every texture on the screen. It's a lot more flexible than that, which is very, very good. Very good news for us. Okay, so we can grab out... Actually, this breaks the table formatting, never mind. Apparently that doesn't like pre-formatted stuff. So we read this out. So the first thing to do is to grab the first 18 bytes, right? And then we say BV. Unpack. Header bytes. Maybe we'll call this like header format or something. And it is a constant, so I like the capitalization for it. So now, unfortunately, this isn't the best way, and maybe actually, I keep talking over myself, right? I keep having new ideas about this as I go. So let's make a TGA header class, but this isn't really going to be a class. This is just going to be a data container. Right, so this is going to have the things that a TGA header has. So self, we have an ID len, we have a col map type. You're meant to do underscores in Python, aren't you? Image type, col map. Let's just call it col spec. So we'll have another object for this, right? img spec. Cool. Self.id id len equals. Let's not even go with underscores, right? Let's just go id len equals id len dot col map type equals col map type self dot image. Cool. And we're not going to do anything else with this, right? So the image specification, the color map specification is probably more interesting. The image specification, we have an X origin, we have a Y origin, we have a width, we have a height, we have bits per pix, and then we have a descriptor byte. I don't know. Self.x origin equals XO, self.y origin equals YO, self.width. I guess I'll call it bits per pixel. I like the name BPP here, but BPP can be bits per pixel or bytes per pixel. Yeah. Isn't there a decorator to make it easy to use a class as a data holder? Probably. There probably is a better, more Pythonic way of doing this. I don't know it off the top of my head, so we'll survive. And then I don't know what this descriptor... Oh, right, it's where the origin is. Yeah, cool. We'll store it, but I think not check it. Oh no, we will check it because we want this to be a 1. I think we just assume that it's upper left. Anyway, we'll add that check at some point. Class TGA color spec. And this just has map origin, map len, entry size, entry bits. We'll go bits, because again, intuitively for me at least, this would be in bytes, but it is in bits. And and these are going to be 32 in our case almost always, but we'll still have it. Self.map origin equals map origin cool. So this is everything we unpack from this field, right? Now we just need to get it in the structure. So let's try to let's do it in this function. Header values. This is good. This is good. So then let's say header equals TGA header. Okay, TGA header. So we have idlen, which is, I need to give this a shorter name because I'm going to type it so many times, so we'll just call it v naught, right? The first field of v. So we're going to go through, and this is how you access things from this decoded struct. They're just in a tuple. I think we just access them with a dumb accessor. So, yeah, v naught. And there may be a smarter way to do this again, but we'll survive. So this is going to be v0, v1, v2, and then we make a color specification. This has v3, v4, and v5, and then the image spec. V6, V7, V8, V9, V10, 6, 7, 8, 9, 10, 11. That's actually not as gross as I thought it would be. And let's double check here. 1, 2, 3, 4, 5. Sorry, I counted a header there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, because we're zero index. Perfect. Perfect. Google says maybe to just use a dictionary. I'm not going to use a dictionary because the ergonomics on Python dictionaries are a little bit gross for this kind of thing. Marginally, do I ever use an interactive hex editor? No, I don't do a lot of hex editing. When I do have to hex edit something, and let's, for example, show this off because this is actually going to be very relevant very shortly. So I've got an asset in here. I've got it called... What did I call it? I exported this as something. Yeah, CLUT test, that's it. CLUT test, cool. So let's have a look at the hex data for this. So I use a program called xxd asset clut test, and then I just pipe this into less. And this is all the hex editing capability I need. You will see that, maybe you won't see that, this doesn't have any alpha information. This is a 24-bit image, which is going to be a problem for us. But it would be cool in our tooling if we could convert a 24-bit image to a 32-bit one. It would also be good if in our loader logic in the PlayStation 2 we supported 24-bit images, but we're not quite there yet. We will get there, we're not quite there yet. Anyway, we're going to pass in the color spec, and we're going to pass in the image spec. And now we have a header. We have a header that we can interact with through like higher level names. That's really, really cool. So, now we move on to the next logical thing to do, the image identification field, right? So we're basically going to skip this, I guess. It's usually omitted after 255 characters. I guess we'll grab it out, so let's go ident equals header bytes. This goes from byte 18 to byte whatever the length of it is. So we might end up with 18 plus 0. That's what this is saying would usually happen, but anyway. Let's also make a head, which will be 18, right? head is maybe a bad name because we have a header, but what will survive? Col data equals header. Sorry, it's not header bytes, is it? It's b. B, and then head is going to be equal to head plus header.id len b head to head plus header dot. We don't get a color map length specifically, do we? Do we? We do. We get a color map length. Integer count of map entries. So this is a number, so we have to multiply this number by the map size. So let's say col map size equals header dot col spec dot map len times header dot col spec dot entry bits. It's the number of bits divided by 8, right? So the number of bytes. How many bytes is this? So grab out the whole color map, and then the head is going to be equal to the head plus col map size. And similarly, I guess the image doesn't actually tell us the size of the image. All fields are unsigned. The low order byte of a 2-byte field is stored first. It's a little endian. The little end goes first. The little end goes first. Okay, that's good, that's good. Image size. So this also we have to calculate, right? We don't get told this. Okay, so the image size equals header dot image spec dot width times header dot image spec dot height times, similarly to before, header dot image spec dot bits per pix integer divided by 8, right? So the number of bytes per pixel multiplied by the number of pixels in the image, and then we do the same thing. Image data equals b head to head plus image size, and then anything left should be the footer that we can just safely ignore. So then we can, now here's the question, do we try to, we have to, because the image, so the color map data, entry color map entry 2, 3 or 4. Entries of each color map entry is 2, 3 or 4 bytes. Unused bits, I shouldn't specify attribute bits. 4-byte entry contains 1 byte for blue, 1 byte for green, 1 byte for red, 1 byte of attribute information. That's really interesting. Again, we don't actually have to like respect this. We can put whatever the hell we want in this file, but we will stick to spec. We will stick to spec. So we need to actually parse out the image data and the color data. A 2-byte field. Fields are unsigned. So we can go image formats, right? We can make a list out of these. If the number of bytes per pixel is 0, then we can just say like we don't unpack anything. If the number of bytes per pixel, and that should actually probably be an error, but anyway, if the number of bytes per pixel is 2, then we go for unsigned shorts, and we go for a list of them, which we can do. I think we can tell it there's a list. Maybe not. Name size, blah, blah, blah. Wait. Pad byte, car. Unsigned car, bool, social, size. Float, blah, blah, blah. I thought we could say there were multiple bytes. Bang is X, one of the integer formats, X outside the valid range. P finding a Pascal string. True or false, that's cool. I thought we could do that. Python struct unpack Oh, maybe we can't. Struct.iter unpack. Iter unpack. Iter unpack the buffer according to the format string. Format function is an iterator which will read equally sized chunks from the buffer until all its content is consumed. That is actually exactly what we want, right? So we just want to take an iterator and turn it into a list. That's fine. That works. That works. That works beautifully. So if it's 1 byte, then we just take an unsigned car. If it's 2 bytes, we take an unsigned short, and if it's 3 bytes, we take an unsigned integer, and if it's 4 bytes, we also take an unsigned integer. They're the same. They're not tight. Oh no, in an image, they're not tightly packed, are they? That's not as simple as I thought. That's only in the color map data, right? So B H. We can't. So I want to apply a function which just grabs out, you know, all of the bytes, all of the integers, all the whatevers, but because the 3 byte chunks aren't nicely aligned and there is no struct type which has 3. So the problem is this. Let me draw a picture. I should be drawing more pictures. If we have pixel data, let's call our pixels A, B, let's call that bytes, sorry. Let's go 0, 1, 2, 3, 4, 5, 6, 7, 8, ... Okay, so if we're in a world where we're parsing, say, 2 byte image data, right? 2 byte RGB data. Beautiful. You can just grab out all the pairs of bytes and you can interpret them. And the Python struct library happily gives you functions that let you pull out all the pairs like this. Similarly, if it's 4 bytes, easy. We can just do it in groups of 4 instead. If it's 1 byte, that's even more trivial. We just take every individual byte. And this function iter unpack is going to be more than happy to let us do that. Beautiful. Beautiful. The problem is that TGAs can also support 3 byte packing. Now this seemingly is not supported, right? There's no 3 byte integer type. And it's to do with alignment, because this is the start of a word, and this is the start of a word, and this is the start of a word. But we're at a different spot every single time. So we can handle this, we just have to do it ourselves. And we'll have to write a function to do it. But that's not hard. So def handle TGA Image. And this is, we're going to take in the number of bytes per pixel, and we're going to take in the image data. Right, so this is a slice of a byte array. So I guess we could say if BPP equals 1 or BPP equals 2. Well, if BPP equals 1, this is easy. We just say return list struct.iter unpack B image data, right? We just use this mechanism. Similarly, if elif BPP equals 2, then we return list struct.iter unpack H image data. elif BPP equals 3, special case, raise exception unimplemented. Elif BPP equals 4, then we can do the same thing again, because we have a type for this, struct.iter unpack I image data, else raise exception. Beautiful. So then we can just return TGA. And our TGA is going to have the header, it's going to have the ident, sure, why not? We're going to convert this to a or we're not going to convert it to a string. Hold on, that's not how this works in Python. Python A, B, C, D, E. I don't think I can just convert this straight to a string, or I think it's not what I want. X dot encode, decode. It's one of these functions, right? It's an encode or a decode. A few people stopping by in chat as well. Enrique Garcia, welcome. Thank you for stopping by. Salty Doubts, great to see you as always. For the sake of curiosity in the data holder topic, I might fancy named tuples. Yeah, what I'm basically doing is a named tuple. Syntax of dictionaries. Yeah, I probably should be using a named tuple. I've used them. I might have used them already in this project even. I don't know. I think I have shown them on stream. I just don't do loads of Python these days. There is it decode? Yeah, here we go, UTF-8. This is one of the weird things about byte string handling in Python 3. You have to do this decode encode stuff. Ident.decode UTF-8. It's actually probably an ASCII string, right? It's probably not UTF-8. I don't know what the spec says. I'm going to assume ASCII. Which I guess UTF-8 is fine as well. Then let's say handle TGA image data. The BPP is going to be header.image spec.bytes per pix. And the image data is going to be image data. Let's split this out to a new line. Let's do this all on new lines. That should look a little bit neater. And then call spec entry. What did I call this? Entry bits. Entry bits? These are entry. Yeah, entry bits. Okay, I'll rejig it. Cool. So we're going to do a similar thing with the TGA here, right? It's going to have a header, it's going to have an ident, it's going to have a color map section, it's going to have image data. I guess the color map should technically come first because of how these are ordered in the real world. I think Python's fine with trailing commas, right? Whatever. Equals bits per pix. We're just going to do this calculation here. It's a bit clearer. Def handle TGA col map. Let's go again. Bits per pix image data. And we'll do the same thing. I'm gonna copy and paste. I'm gonna copy and paste. There's no real reason to do this, except we want to change this from image data to col data. Awesome. So we've got our bytes per pixel, except now in the case of 3, we want to do the same thing as 4. Because that's what the spec says happens with this, right? If the color map 3-bit entries contain... Wait, did I not just... What did I just read? What? I swear I just read something that said there was an extra byte in it. Okay, never mind. I will undo what I did. I read something that didn't exist. These things happen. These things happen. So, there should be enough to parse a TGA once I define a new class for it. We'll get rid of this. I guess we'll capitalize it. I don't know if that's really the best way to go, but sure. Self, header, ident, img, map. Cool. And so we should be able to do this now. If we have a loaded binary TGA. So sure, let's call it palletize. So if this is our main file, we're gonna import sys. I guess I'll do this up here. I tend to like only importing sys if we're in like this block, if we're in our main thing, but that really only matters for scripts that have more than this, and this script won't. Cool. So yeah, let's just with open with whatever we pass in on the command line, which we're going to read in binary mode as f. Going to read all the bytes. We're going to call parse on it. Parse bb. And let's just see what happens. Asset. Okay, so unpack requires a buffer of 20 bytes. That means that this doesn't add up to what we're saying it should. So we're saying this should take 18 bytes, right? And when I counted here, so 1 plus 1 plus 1, so 1, 2, 3. Did I just count the number of things? 1, 2, 3, 5, 7, 9, 11, 13, 15, 17, 18, 19. Yeah, okay, that means it is actually the first 20 bytes, isn't it? Cool. Actually, the other thing we can do, if I didn't just bloody close that, I think, yeah, that calc size method, right? Calc size returns the size of the struct, yeah. Let's do that instead. Struct.calc size. Let's do away with magic numbers entirely. Cool, so we can swap back to this other awesome file. We can run our awesome file. We can maybe run our awesome file. Bits per pix. Did I mean bits per pixel? Okay, so I wrote this name out better than I give myself credit for. Bits per pix. L. Pix. L. Unsupported BPP and image data 0. That seems like we're unpacking things incorrectly. So let's go into where we're defining this header and let's give it def. Let's give it a string implementation so we can print it out and see what's happening in it. So let's go self dot, let's go print, return a format string. We'll go, maybe we need to wrap it in some kind of bracket. Let's go ankle braces. Length of ID equals self dot ID len. Equals self.col map type equals self.image type, and then we've got this sub structure. We'll go with this for now. And after we've created it, let's go print header. What does this do? Let me I know, let's keep doing this. In parse, in handle color map. So this should get printed. It does. It does. Image type equals 1. Awesome. I love it. Let's go. Self.col spec. So we'll add a string representation for these things as well. Just so we get something printed out nicely. Maybe we should put a new line in there as well. Cool. Image spec. I think maybe named tuples would have a better default for this, but I want to... I don't know. I don't know if a named tuple syntax is going to be as readable as this. Let's just go... I guess we won't use those brackets. Hey, we'll just go self.xOrigin, self.y. We'll do less for these, right? Because they're just simpler. Oh, no, maybe not simpler, but I think they have a more intuitive order than the other header structure. So print, not even print, return self dot map origin cool. Let's see what happens if we run it. So what's this saying? This is saying... This is probably more useful as... Oh, is it? Color map origin. Integer index of first color map entry. I don't know what this means. I don't know how to interpret this. Color map length. Number of color map entries. So this is probably also wrong. This is certainly wrong. 16. So this is off. This is saying the Y origin is 16. This is off by a byte, or by 2 bytes, because this should be 0, 0, 16, 16, right? But then I don't know what this is. Is this? Well, but I guess the bottom... Maybe we're interpreting these in the wrong order? I don't know. This also feels wrong. Again, this seems like we're interpreting 2 bytes together as one bigger byte, right? So this should be 1... This still seems like too many things. Still seems like way too many things. Number of bits stored in a single pixel. This should be 24, right? So that should be 24 in hex. Hold on. Should be 1.8. So that this is actually where are we? Where'd we go? That it was actually quite close. That was actually quite close. Okay, time to go back to the drawing board. So ID is 0, that's good. CM type is 0, that's also good. We're gonna go back into our dump. If I can get control of this editor. So, first byte 0, yes. Second byte 1, yes. Third byte 1, yes. First byte 0, second byte 1, third byte 1, yes. And then something goes horribly wrong. Something goes horribly wrong. This should be 0, 0. Why is this not 0, 0? Okay. Why do we jump? Why do we make this jump? Why do we seemingly... Where do we go? Where do we get 4096 from? Where could that come from? 4096. 4096. 4096 is 2 to the... 4096. 4096. Let's... 4096 equals 2048 times 2 equals 2 to the 11 times 2? Because 2 to the 10 is 1024, right? So 2 to the 11, so 2 to the 12, sorry, equals 2 to the 12, right? So this gives us 1000000000. So we should see a 200 or a something with this bit set. But so yeah, the only way we can get this 2000, right? 0200. This pattern has to be in the file somewhere. Where is this bit coming from? This sums up my feelings right now. Okay, let's go back to our format and double check it, right? We've got to be doing something weird. Oh, well, the other thing that we can be doing here, of course. Oh, no, am I dividing? No, this checks out. BBB, HH. Let me double check what H means, okay? It's also, I could specify this as little endian. I think that's correct, right? What if I say little endian and rerun it? Is that gonna... right, yeah. I'm not in the right file. That seems more promising. That seems very promising. Okay, let's double check here. Do I have anything sus in my history? Hopefully not. I usually restart my browser before I start the stream, right? It's all fine. Trying to learn something. That's something about this or just in general. Okay, so what are we seeing here? 0, 1 1, yes. 0, yes. 1 0, no. 0 0, no. Yes. Wait. 1 0. Oh wait, no, hold on. What's 1 0? Yeah, 1 0 is 16. No, never mind me. 24. I don't know where this 24 comes from. So 1 2 3. 1 2 3 4 5 6 4 5 1 2 3 4 5 1 2 3 1 2 3 1 2 3 4 Oh, the color map origin is 2 bytes. Sorry, no, that was actually correct then. So 1 2 3 and then this is 2 bytes. This is 2 bytes. So that's 0. Then this is 2 bytes. That is 16. This is 2 bytes. Wait, is it? Wait, no. That's not 16. That's only 16 if it's, but it's little endian. So this is actually, so this value 1000, right? Where we see 1000, we have to convert that in our minds to 0010, because it's little endian. So yeah, that is actually correct. 100. Similarly, this is 16 plus 8, which checks out to be 24, because I know my 8 times tables. 0. 0. Wait, 0. 3, 4. 5. Sorry, 5, and then this is 1 byte. So then we get 0, 0, width, height, 16, 16. That's all beautiful. And then how many bits per image pixel size, image descriptor byte? Where are we? Width, height, image descriptor, image pixel size, number of bits stored in the pixel index. 8 bits. This is saying it's 1 byte color? What? That doesn't feel right. And then the image descriptor byte, sure, has some stuff set. I should print this out in hex, not in decimal. This is 100000. So bit 5. This is saying that the origin is in the upper left hand corner. Setu12, welcome. Thank you for stopping by. We are learning about TGA. I've already got a TGA Parser. I'm rewriting one in Python because we're going to make it part of the asset pipeline. Cool. Wait, so, but if I do this, yeah? If I do this, why does this say unimplemented? Because 8.1, TGA with parse, handle color map, line 88 unimplemented. Oh, because, yeah, we have, we have too much data in our color map, right? We have 24 bits per pixel in our color map. Ah, interesting. Okay. So this claims to actually have a color map. Right? This claims to actually have a 16 color map. So, I thought, the whole point of this was that I thought a Sprite didn't do this. Apparently it does. Apparently it does. Interesting. Still good to know and still good to be able to play around with, because we're going to need to be able to... So let me pivot here, okay? Let me pivot. This has been a weird stream. I'm going to... Oh, the other thing I should do here. It's probably actually... that's not really going to work. Okay, anyway, no, sorry. I'm getting distracted again. We're going to pivot here. We're going to say rather than obsessing with... Sorry, I'm getting a phone call. I'm going to have to BRB, and then we'll pivot. Okay, we're back. We're back. Thank you everyone who bears with me through that. Awesome, sorry, I just lost chat for a second there. So, we're gonna pivot, okay? We're gonna pivot. Rather than processing these to make sure that they have color palette information and to convert to index color, we're gonna potentially strip out the color map so that these files are smaller to load into the PlayStation 2 main memory, and we are going to export the color map into separate files. I think that makes a lot more sense as far as my brain goes. We are going to make kind of static assertions at build time that the files use the palettes we think they do. That is my general idea, right? And make sure that, you know, yeah, kind of describe all of our data up front, have a manifest that says these things should be compatible with these palettes, should contain these palettes in their raw files, but then when we load them into PlayStation 2 memory, we can basically do whatever we want with them and apply whatever palette we want. set 12. I'm writing my own TGA Parser. It's not that impressive, okay? It's a very, very simple spec. There's not a lot to it. There are 100 lines of Python code, and this is it. This is everything parsed. Pretty much, apart from handling this edge case of 3 bits per pixel, but we're going to do that now. What the hell is a TGA? TGA target image. Very, very simple image specification, very easy to load, very easy to work with. They're what I'm using as my default for now. If I need to have like more compressed image data in the future, sure, maybe, but we'll go with this. Very, very easy to work with, right? So again, I've already got a C parser for this. It is a similar length to the Python one, including all of my Lua bindings, right? The actual parser itself is literally this function here. So we're looking at what, like 40 lines of code, maybe? It's so easy to do with. It's so easy to do with. And yeah, because it's so easy, it's one of my favorite image formats. So if we have 3 bits per pixel, let's write a different function for this. Let's call it 3ify. Let's call it 3ify. I think that's a valid name. Okay, so while h less than the length of d, so we're going to go through every byte of d basically, but steps of 3 at a time. And actually there might be a Pythonic way to do this. Python partition list. There's some format. Hold on. Let me just experiment for a second here, because there's something in my brain that's telling me. So we have this syntax in Python where you can say, like, give me everything from the second element on, give me everything up to the second element, but you can also say, give me every even element, give me every third element. So this, So we can say give me every third element from this list, then we can say give me every third element from this list offset by 1, then give me every third element of this list offset by 2. And what I'm seeing here is, well, this is going to give us, you know, if we imagine these are grouped together, 1, 2, 3, 4, 5, 6, 7, 8, 9, this is going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9. So the 0th index of these 3 lists is our first triple. The first index of these lists is our second triple. So let's actually, let's do this instead. So let's say firsts is going to be D every third index. The seconds is going to be this offset by 1. And the thirds is going to be this offset by 2. So then we go for I in range. So for every index in the first list, because this is going to mean that we always consume group. Like they're all going to have groups of 3 as long as the length isn't equal to 1 or wait, which one? I guess we want to probably do it. I guess we want to do in length the length of thirds, right? Or do we just want to assert up front if len firsts not equal to len seconds, or len firsts not equal to len thirds. Does this then raise exception unbalanced pixel data not a multiple of 3. Right, so if this isn't equal to 0 modulo 3, then these 3 lists won't have the same number of elements. We need them to have the same number of elements. We're going to assert that up front, so then we don't need to worry about one of these lists being longer than the other or something like that. And if one is going to be longer, it's going to be firsts. So if we didn't want to check that, we would just do thirds. If we wanted to kind of silently ignore any extra pixels, we would just go over the thirds list. But anyway, we're going to change this back to firsts because it's a bit clearer. Px equals, we're going to go firsts. Actually, let's go little endian, right? So blue comes first, red comes first. What comes first? Let's say let's say red. Seconds I, and then B is going to be we also need an output list, don't we? Out equals just some dumb array. Out dot append, and it's going to be R plus G times 5 left shift through. Does Python have bitwise operators? It does. So let's go R or G left shift by. I really hope this is the right order. I actually don't think it is. I think it's B G left shift 8. B G left shift 8 R left shift 16. Cool. So now instead of this, we return 3fi curl data. And now we can do the same thing with the image data as well. Are these literally the same function? They are literally the same function now. So handle, we're going to call this handle pixels, and we're going to delete the duplicate. So we could probably do that in inline now. Handle cool. Let's actually go to the right file. Oops. Oh dear. I did that to the wrong thing. Now I need to change this to an I, and now when I run this, it's just going to work. There's going to be no problems. Nothing is going to go wrong because image data helps if you run that in the right file. What did that do? And that works. Perfect. Perfect. So let's get rid of this print. Nice. So now we're just going to get the header printed out. This all looks good. Can we reassemble this? Let's try and reassemble a target and then load it into a sprite and see if we get the same thing out. This is the test, right? This is when you know you've actually done it. So we can pack this back together. We need an un3ify, right? So let's go. So we need the opposite of this function. We need one that goes through a list, that pulls out the pixels. So for pixels, for p in pixels, out equals byte array. For p in pixels, b equals p and ff, g equals p right shift 8 and ff, r equals p right shift 16 and ff. We don't actually need to end ff this. We'll end ff that one just to be safe. And then we say out.append wait. I think these names are wrong, right? Which one comes first? Okay, well let's try this. Have I been introduced to beta Twitch TV yet? I know of it. I haven't really done much with it. I don't know. I'm not a big emote guy. I do have affiliate. I do need to get that set up and get some emotes on my channel, but yeah, I don't know. I'm not the biggest meme lord out there. I'm not much of a BTTV guy. I don't really know much about it other than the extra emotes. I do actually want to write my own chat viewer though. That is in my goals, but I don't know how I'll handle emotes in it. Do I go the extra step and have the like API support to pull custom emotes down? Maybe. We'll see. Okay, so this function will do the opposite of this function, right? Un3ify of 3ify of D should give us back the original D. I like this. Maybe there could be an emote that's just a red triangle. I spent so long trying to get one single red triangle to draw on the PlayStation 2. That would be very fitting. I don't know, I need someone to do some like cool pixel art of like me as a person, right? Like just a beardy dude. That would be fun. That would be fun. But I do have some friends who are very talented artists. I'll get something happening soon, but it'll take time. It'll take time. Okay, so let's def right. So the first thing we do is to header bytes equals struct.pack. So we give the format string, which is header fmt, and we give this all of the stuff it needs. So let's go up to where we grab this out. We're not actually going to keep this here, this is just for reference. So we go header.idlen, header. I'm going to do these on new lines, it's just easier. Header dot, what was the second thing called? Col map type. Oh man, there's a Unicode red triangle, that's awesome. What's the main difference between the graphic synthesizer and an ordinary GPU? Everything. The graphic synthesizer is barely what you would consider a GPU by modern standards. It's a rasterizer. It can draw triangles really, really well. It can texture those triangles, but it doesn't have shaders, for example, right? It's a fixed pipeline processor. There's no fragment shader. The PlayStation 2 has no fragment shader capabilities at all. If you want to do per fragment operations, the only way you can achieve anything like that is to sample the frame buffer back into main memory, run some like post-processing whatever on the main CPU, then re-upload that to VRAM again, which is very, very slow. It chews up a chunk of your frame time. The CPU operations are really like costly. So you do that only if you absolutely need to, otherwise you find other weird hacks. So that kind of limits the PlayStation 2's ability to run certain effects that the Xbox, for example, was very good at. The PlayStation 2 has unparalleled vertex processing capability, but none of that happens on the GPU. That all happens on specialized vertex units, vector units, sorry, which are part of the main CPU, but like completely independent processors with their own ISA. So the GS is not very powerful. It's very, very limited, but it does what it does extremely well. It can pump out a crap load of triangles. One of the cool properties of the graphic synthesizer is that it's very, very good at overdraw, right? It's so good at just pumping out triangles that in lots of cases, developers found it was more efficient to not waste CPU time testing things for visibility, to just overdraw, to just not worry about overdraw, to just throw triangles at the processor. It was so good at processing those triangles that you could just, you could save work where on other consoles you would do like complicated CPU algorithms to work out what should be in the scene and what isn't. On the PS2 you just throw it at the rasterizer and see what happens, which is fun. Fun little tangent there. I love the graphic synthesizer. It's a great piece of hardware. It does what it does extremely well. Okay, so the image type, and then we get into the color spec. So head.color spec. Sorry, this is TGA.header, 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 TGA.header. Alright, color spec, map origin, map blend, entry bits, TGA.map origin, TGA.map len, TGA.map image spec dot x origin TGA dot header dot image spec dot y origin. So the scene's rendered on the CPU and the GS makes it 2D? No. The 3D stuff, the 3D maths happens between the CPU and the graphic synthesizer in specialized processors. The graphic synthesizer, it is kind of like a 2D draw. It does a depth test, so it has a Z buffer. It does anti-aliasing, it does texturing, so saying it's rendered on the CPU isn't accurate. But all of the calculations, all of the vertex stuff, I mean, you know, you have to massage the data from like floating point vertices into a fixed point format that the graphic synthesizer understands. All that happens before the GS, but the GS definitely does more than just making it 2D, but it's fixed pipeline, so what it can do is kind of limited. The graphic synthesizer also isn't responsible for signal generation. That is another hardware component which is meticulously detailed in the hardware manuals, and I don't really know why anyone would need to know any of those things, but the signal generation stuff is separate because this is still an analog console at the end of the day. Image spec.width, TGA.header.image, image spec.height. Oh, what time is it? Oh yeah, I should probably get going in a minute. Let's see if header.image spec.desk. Analog console. The PlayStation 2 has analog output, right? It outputs an analog video signal, not a digital video signal. It outputs analog audio, not digital audio. So that means that there is a specialized component which generates the waveform signals that get output to your TV. It's an important distinction to make. Actually, I think the PS2 does have digital audio output in some cases, but anyway. It is ultimately an analog console. It's doing things in a very analog way. So we've got our header bytes, and because I'm running out of time, we're going to print the header bytes. That's going to be, return the header bytes, and then we're going to print them out, and we're going to be happy if it matches, right? So let's go import parse, right, equals right TGA print nh. V is not defined because we kept some crap in this function which is not needed. TGA cult spec has no attribute entry len. I have called this the wrong thing. Entry size? Entry bits. That makes sense. Python required argument is not an integer. Now that is interesting. Why is that? In right. Required argument is not an integer. ID len, color map type, image type. Ah, yes, that would make sense, wouldn't it? Map origin, map length 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think that is everything we need. Expected 12 items to pack and got 11. Okay, so what am I missing? What am I missing? 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 1, 2, 3. 1, 2, 3, 4, 5. I'm missing the bits per pixel. Yep, every time. Every bloody time. Okay, now we can compare this. We can compare this to what we saw before. 0001, 0100, this is good. 0001, yes. 0018, yes. 0000, yes. 0000, yes. 0100, 0100, 08. Yes, perfect. So it didn't get quite as much done in this stream as I'd hoped, but this is a TGA parser, which we'll be able to put to use, massaging assets into the formats that we want them in, and then writing them back out. So we can do color conversions, we can do all kinds of interesting stuff, right? But I think what will be especially interesting is to be able to take a TGA and dump the palette either into another TGA image with the color map as image info, or maybe it's color map info, I don't think it really matters, but just somewhere where we can load it out and use it, or maybe just directly into a binary format where we can just load it straight into the PS2 memory and then dump it straight into VRAM from there. And we can do the same thing with TGAs, by the way, and in some cases, with some textures, we may actually want to pre-process these into a binary format. We open the file, we know ahead of time its entire length because we've pre-processed it. You know, we have that in some manifest somewhere again. We can just load it directly into PlayStation 2 RAM and then just copy that directly into VRAM, right? Pre-process it, have the bits ready to go. Then you don't spend any time at runtime, you know, loading, doing anything else. You do one read call into the file and that's it, you're ready to go. One thing I do like about TGAs is that it only takes 2 read calls into the file to read all of the pixel data, so that's not too bad, but yeah, if we need more performance with some textures in some situations, we always have that option. So it's important, I think, especially for a retro console project, to have a good pipeline for processing your data. And TGA and .obj are 2 amazingly simple formats to work with. You know, in 40-ish minutes, how long's the stream gone for? Just an hour and 20 minutes to get this tidied up and the reverse working. That's beautiful. So I'm going to get this tested off camera. I'm going to make sure it works and that my texture loading is good. I suspect that this is actually why some things weren't working in a previous stream. The best looking textures shared a 16 color palette on the PS2. That is an interesting claim. But I imagine, yeah, like if you want that texture detail, the only way you're going to get it is by using restricted color palettes, right? 16 color palette, yeah. And there are lots of creative things you can do, and I'm excited to play around with it because you can use vertex color on top of this. So really, the sky is the limit. It's all fun stuff to play with. So thank you very much for tuning in. I've been Tom. This has been really good fun. I think we still have a few viewers kicking around. We do. Let's throw a raid over to someone. But for everyone watching on YouTube, I'll catch you next time.